Oi, Bia, tudo bom? Eu não sei se você me conhece.
Ah, o Gwen fala direto de ti.
Ensinei vários nomes feios pra ele no grupo.
Fala todos os palavrões que tu ensina pra ele. E
Você
aí, tá
trabalha...
tudo bem?
Hã?
Tudo bem por aí?
Tudo bem. E você?
Nossa, tudo bem também.
Você trabalhou com a Olga, né? No
Trabalhei
seu...
com a obra no
Legal,
mestrado.
legal. Acho que eu li sua tese quando eu estava fazendo a minha. Bem legal.
Nossa. Eu tava até pensando, lembrando de ti ontem, porque eu trabalho com uma aluna lá no Caltech, ela é aluna do Andy Thompson.
Ah, Luna,
Luna,
Vale? Isso,
aluna.
legal.
E aí a gente ela submeteu um paper dela e o Hyodae chegou aí. Ah, mas depois a gente conversa. Hey there.
Hi, Bia, how are you?
I'm good. How are you?
You hosting today?
Yeah, I'm hosting today. Sarah is on an airplane, so.
Okay, great.
Do you want to try to share your screen just so we're sure everything's working?
Mhm.
Cool. How are you doing, Hyodae?
Good. I'm disabled to participate. I'm
Oh,
able to share. So,
okay. Uh, how about now?
yep. Right.
Awesome.
Let
Yeah,
me
it looks good.
try this one. Then move this out of the way. My here. So this is me.
Yeah, it looks great.
Okay, great. 40-ish minute, 30. 40.
It's up to you. Like we have an hour slot, and usually people shoot for 30 minutes and we have discussion, but we have an hour, so it's really up to you.
I shoot for like 40. I prepare for like 40-ish minute talk.
Okay, yeah, sounds good.
And I since you're here, I wanted to show this plot on the right, which is I got it from your talk, and I
Yeah.
couldn't where you got it. Maybe that's from your from the proposal,
It's
or
from the proposal.
I should have asked you if it's okay to use this.
It is okay to use, and actually we were talking about it yesterday. So the version of the proposal was due yesterday, and Sarah mentioned that you had borrowed this figure, and
Okay.
it seems like it's not as self-explaining as we would like it to be. So we were working on a different version. So if you have any feedback.
Yeah, so my comment here is, I guess, I think the point that I tried to make from this talk is that we need a heat flux to say something about this ABL, like you see the cloud response boundary height adjustment on the small scale near the currents. You need to say something about heat flux as well, because what drives this boundary layer stratification is through turbulent heat flux, not necessarily momentum flux. If it's purely momentum flux, it has to have a strong stratification that can mix across the temperature anomalies. But if it's convective regimes, then you definitely need heat flux to generate this kind of perturbation in the boundary layer. Let's see how it goes. I try to link this butterfly and Odyssey. Just so it kind of makes sense. Butterfly measure heat flux, Odyssey measure wind stress. The surface current. Both. You need both components, right? You need to have a surface current to measure heat flux, estimate heat flux. You need to say something about wind impact, current impact on wind. You need heat flux as well. So let's see how it goes.
Okay.
Okay.
Yeah, no, I think that particular figure we're trying to folks are starting to get here, but it's basically a competing hypothesis that the effects of relative wind is local versus like you see a signature in the far field.
Okay. So
And so
there's
that only makes sense when you got the two figures. So that's just one panel of a two-panel
okay.
figure.
Okay, sure. I should have known that then. I should have had this up like hypothesis B. I apologize. I didn't have the access to the
it's
figure.
completely fine. But I would be happy to talk more about it later because we would love to hear more about what you think.
Okay. Yeah. Okay. Great. It's really good to know there's a competing hypothesis. Then. Yeah. Okay.
Just gonna wait one more minute. Hyodae, folks are still coming in.
Sure. And is my audio okay? Right?
Your audio is okay. Yeah. All right. Good morning, everyone. It's a pleasure to introduce Hyodae from Hui, who's gonna give this week's Odyssey webinar. And without further ado, Hyodae, please take it away.
Okay. Thank you very much, Bia. Yeah. So thank you for opportunity for me to give a presentation today. So my title here is the wind current coupling in the context of mesoscale and frontal-scale Earth interaction. And I think when I meant by wind current coupling, I have very much in mind the Odyssey mission. And when I say mesoscale and frontal-scale Earth interaction is something more traditionally referred to as LC heat flux response to mesoscale SST variabilities. And I think, of course, coupled system is complex and it involves both the momentum LC heat flux to invoke the LC interactions. So I think I tried to make a point that the LC wind current coupling can be only understood in the context of LC heat exchange as well, and vice versa. So before we start my presentation, this is our review paper recently published in Journal Climate. This is the work led by US CLIVAR LC Interaction Working Group. And many of the co-authors are involved in Odyssey mission, as well as climate community. So, and this is a very comprehensive review of all aspects of Earth's interaction related to ocean mesoscale variability. So when you have ocean eddies and fronts, what does it to Earth's heat and momentum fluxes, and what does it to local atmospheric boundary layer, and then as well as a tropospheric variability in the much larger scale at the mesoscale variability, and then how does it feed back onto the oceans? So if you're interested, take a look at this paper. I'm going to use some of the figures from this paper to talk about mesoscale Earth interaction processes. Yeah, so okay, I'd like to thank Larry O'Neill, who's a co-chair of the working group with me, leading a large group of people here, as well as the whole working group. All these 16 people contribute to the paper. And also I'd like to thank my postdoc Sijar and then my colleagues in Korea, Ajin Cho and Ha-Jun Song, I'll talk about their work a little bit. So, I think some of you are already very familiar with this kind of map, mesoscale, at oceanic mesoscale. So scale maybe 10 to 1,000 kilometer. We all know the ocean is driving the atmospheric variability, and that is mostly due to air-sea heat flux. But because we don't have global mesoscale resolving air heat flux measurement, we've been using the scatterometer winds and microwave or AVHRC subtemperature, microwave subtemperature to say something about their coupling. So in the left plot is a map of correlation between wind speed and sea subtemperature after they are spatially high pass filtered to pass only a scale smaller than 10 degrees, so about 1,000 kilometer. So this is our broad definition of mesoscale in the ocean. So if you do this relationship between SST and wind at oceanic mesoscale, you have this very dominant positive correlation globally, pretty much everywhere. And this positive correlation indicates that the places where ocean influence the atmosphere. So you can understand this positive relationship as a kind of warm SST increase the wind speed, cold SST decrease the wind speed, and that's because of boundary layer stability adjustment or secondary circulation in the boundary layer, but that is all mostly because of heat flux response to SST. And you can see positive correlations are strongest in major ocean, dynamically rich regions of world ocean, so western boundary current, Southern Ocean, Arabian Sea, Eastern Pacific, Tropical Pacific, Atlantic Ocean, where tropical instability waves are dominant form of mesoscale variability. So all these are very strong regions of SST fronts and mesoscale activity. You tend to see the very strong atmospheric boundary layer response to sea subtemperatures. But again, because this is a wind and SST correlation, it doesn't say anything about heat flux. So we don't have a good satellite measurement that shows something about global estimate of air heat flux response to SST. On the right, Larry used this ERI5 reanalysis to attempt to calculate the correlation between sea subtemperature and latent heat flux at, again, spatial scale smaller than 1,000 kilometer. So this is a paper used in the review papers. You can get a much more detailed analysis explanation about this figure. But basically, what it shows is that at this small scale, again, mesoscale, sea subtemperature and latent heat flux are negative correlated. So here, negative correlation means warm SST, higher heat flux out of the ocean. So ocean lose heat, atmosphere gains heat. The gain of the heat in the atmosphere is what affect the stratification in the atmosphere boundary layer and changes the wind profiles. So this is sort of consistent, right? And then because the atmosphere responds to heat flux to at the ocean mesoscale, there's a large body of literature that's attempt to suggest that atmospheric circulation does respond to mesoscale variability, especially in the western boundary current region. So the panel, this figure shows a very simple climatological estimate of the storm track. So this is a meridional eddy heat transport at about 2 kilometers above the sea surface by atmospheric reanalysis data. So deep green means a stronger storm activity. And the contours are sea subtemperature climatology. So you can see maximum storm track activity is in the western part of the basin, and they tend to be aligned with strong sea subtemperature gradients or regions of warm sea subtemperature. And this is not coincidence because we know that in the theory, baroclinic growth rate of this extratropical cyclone scales with something called baroclinicity vector, which is related to two terms here, 1 over n. So weaker the stratification, stronger, faster the growth rate of this baroclinic eddy, or the stronger the system temperature gradient. That's whether that's meridional or zonal. You get the strong, faster growth rate of the storms. So these two conditions are met of the western boundary current region, where this kind of semi-permanent western boundary current front, thousands of kilometers in the length scale, they are large enough to modify the stratification and the air temperature gradient at say 2 kilometers over the sea surface, right? So they are very large scale forcing for the low tropospheric baroclinicity, and storms respond to that forcing. So So this is extremely important to understand this, how the stratification is influenced by local warm SST transported by the western boundary current, as well as the spatial distribution of the LC heat flux that determines the differential heating of the atmospheric boundary layer. And then if you talk to meteorologists, they care about this SST distribution. So what they do is that there are a number of studies like this. They run AGCM simulation with a sort of perturbed temperature anomaly. So in these two cases, example here is the top panel is the Kuroshio, and left panel, right panel is Gulf Stream. And they take the two set of AGCM simulation, one with a control simulation, so that's a realistic simulation. And then middle panel is a smooth of temperature, where they smooth out the sharp nature of the SST front. So these are the two different SST. And then ran parallel, and then just look at the storm track response to these different SST distributions. And what they found is sort of consistent with this theory. Locally, where the storm track is climatologically maximum, you tend to see stronger storm track activity just because you have a higher stronger system temperature front, both of the Kuroshio and Gulf Stream. So this is expected by this linear theory of the baroclinic instability in the atmosphere. But also very intriguing fact is that if you go downstream, these studies and other studies also claim that there are very interesting downstream, emerging downstream response in the storm track. So in this case, Kuroshio, North Pacific case, there's I guess the cyclone activity in the Gulf of Alaska. And then in the Gulf Stream, it tend to have this elongated downstream storm track response that affected Western Europe weather pattern. So there's some indication that this local coupling does have a large-scale implication in terms of extratropical cyclone activity. My paper study 2017, we look at this a little bit, and I realized it's not really that simple story that when you're perturbed in the one location, and you expect a predictable response in the downstream in the extratropical atmosphere, and that's because extratropical atmospheric dynamics is highly nonlinear. This is one example here. We ran this atmospheric model with two different SST anomaly, one with scenario, the case where Gulf Stream is shifting northward. If you do that, this is respective system temperature anomaly pattern. So Gulf Stream shift northward, there's a larger positive SST anomaly here, and the opposite anomaly in the north of it. And then, reversely, when Gulf Stream shifts southward, you get this kind of SST anomaly. So what we did is a perturbed atmospheric model with two different SST along with the climatological SST. So we have three sets of very large member ensemble simulations, and then look at the response in precipitation, because precipitation is important for us. And then, but instead of looking at just there are a few ways to look at the response, but what we decided to do is to look at the symmetric component of the total response. Symmetric means that the response in the precipitation is sensitive to sign of the SST forcing. So this is simple formula here. And if you do that, you get this kind of precipitation response that is highly, highly significant. So right off the Gulf Stream here, warm SST leads to higher rainfall, cold SST leads to reduced rainfall. And this is sort of deterministic linear response in the system. And that's because of diabatic forcing of the ocean to the atmosphere. And schematically can be understood here. There's a warm Gulf Stream front here, for example, and the atmospheric cold front passing off this warm front. And behind this cold front, you have this massive heat flux out of the ocean that acts as a diabatic heating of the storm system, and they increase the potential energy of the storm system. And that, of course, that eventually leads to higher rainfall in this right of the maximum SST anomaly. So this is somewhat expected response, right? But what was not expected here is the asymmetric or nonlinear response. This is simple formula again here. So this is a response that is independent of SST anomaly. So no matter whether you perturb atmosphere with this anomaly or this type of anomaly, you get a similar response like this. So in this case, nonlinear response is the decreased rainfall all along this northern part of the basin and increased rainfall southern part of the basin. So this is very intriguing, and we spent a lot of time trying to understand this the process, and we discussed it in depth in the paper, this mechanism, and that involves nonlinear eddy-beam flow interaction in the upper levels of atmosphere. And if you're interested, you can take a look at this paper for more detailed analysis. The whole point here is that in order to evaluate the climate scale impact of the Gulf Stream variability, I think it might be very difficult because of fundamental stochastic nature of the atmospheric variability in the exotropics. And the Arnold Saya 2019 paper and a more recent presentation, he coined this term as a kind of quantum cafe, where there's a kind of upper limit of the atmospheric response to SST forcing in the exotropics. So whole bottom line here is that atmospheric response, especially in the exotropics involving storm track, can be quite complicated, even with the modeling simulations. So, but here still it's very important to understand the air-sea heat fluxes, right? And like I mentioned, we don't have a global estimate of air-sea heat flux direct measurement at a global scale. And we do have a satellite mission that is preparing for this effort. This is Butterfly, and that led by large group of scientists, including myself. And this is basically aimed to provide a simultaneous measurement of all state variables, air temperature, humidity, winds, and SST, that allow you to estimate the air-sea heat flux estimate at global scale at very fine resolution, about 15 to 20 kilometer resolution. And the focus here is, again, very much on the storms, exotropical cyclones here. So when exotropical cyclone like this atmospheric front aligned with the cold front of a system temperature front, the air heat fluxes can be extremely large. And how do you quantify this effect from the global scale? And the hope here is that if you estimate accurately enough this air heat flux over this box, the forcing region, you may have a better chance of predicting large-scale downstream effect of the storms that might affect us on the terrestrial rainfall and things like that. Again, the mechanism here is the mesoscale air heat is out of the ocean for the warm SST, and then cold air heat flux is into the ocean and the cold SST. So this is butterfly concept. And you can compare that with the Odyssey concept. Odyssey is, again, to try to measure surface winds and surface currents simultaneously at the very fine spatial scale and try to understand this momentum coupling, winds and current coupling, right? So on the left, here's a similar kind of correlation map that I did like many years ago. I never published this work, but this is correlation between wind stress curve from quick scatterometer. I think it could be interim or scatterometer, I don't really remember. And the correlation of wind stress curve with the surface vorticity based on abyssal current, geosurface current. If you do that, you get this negative correlation, and this is expected because wind stress curve, surface current is reversely manifesting the wind stress. So when surface vorticity is positive, wind stress curve will be negative. So this is kind of expected result, and you see this the overall very strong negative correlation between vorticity of the current and curve of the stress. And I think Lionel has a paper that shows that surface vorticity is possibly correlate the winds at the surface. So this does indicate that this kind of the surface current impact on surface drag is actually impacting the boundary layer winds. And this is one of the hypotheses that Odyssey, again, Bia and I just talked about this before the same webinar start. There are competing hypotheses, and I only know about this hypothesis where surface current flow, in the presence of very strong surface current, there might be some direct local boundary layer response to this surface current. And I think my point, the point that I like to make here is that the question is, can the Odyssey alone help better understand the surface current impact of the atmosphere? In other words, without knowing the surface heat flux distribution, do we fully understand this boundary layer coupling process involving surface wind and surface current? And I just suggest that the answer might be no. And I think my argument is that we need to have both measurement same time. So this is the one example that I did study when I was a grad student, Scripps 2007 paper. So this is quite a long time ago. We are looking at the tropical instability waves. So we all know tropical instability wave is one of the first process phenomena that we look at in terms of mesoscale areas interaction. We undoubtedly published paper using scatterometer winds. The first thing we look at is a very strong local boundary coupling between over tropical instability wave between wind speed and sea subtemperature anomalies. So this is one example here. EOF between SST and wind stress, combined EOF. So there you see this warm, cold pattern of SST anomalies. So those are the tropical instability wave. And these are the vectors related to wind stress or winds. And you can see the warm SST, there's a winds of all increases given the background southeasterly trade winds and heading northwestward. And of the cold water, wind is opposite or going southeastward. So this is very, one real life example of positive correlation between wind speed and SST anomaly, right? So this is what is expected. Again, this wind response is through the heat flux, not instead of drag modulation of surface drag by surface current. So when I looked at this tropical instability wave, this is one snapshot. So this is tropical Atlantic TIWs in this case. You see it's a warm, cold pattern, SS anomaly. And then there are two arrows here. Green means surface current and black means surface wind or wind stress. So we all know the cold water is pushing northward, warm water is pushing southward as part of TIV, tropical instability vortices. So there's anticyclonic circulation anomaly related to TIWs. And because there's a warm SST anomaly, increase the wind speed locally. So there's an anomalous wind northward of the warm water, anomalous wind southward of the cold water. And this is, again, very simple SST wind coupling process. And that anomalous wind act on the surface current related to tropical instability waves. So cold water is pushing northwards, and warm water pushes southwards. So any given time at TIW time spatial scale, there's a negative correlation between wind stress induced by surface temperature anomaly with the surface current by TIWs themselves. So if you do the correlation between surface current and wind stress anomaly at the meridional direction, especially, you get this very strong negative correlation, and this is indication of negative wind work. So this acts as a sink of the kinetic energy of tropical instability wave. Of course, if you allow spatially uniform winds over TIW, you get this negative wind work as well because the wind stress is affected by surface current. But here is this magnitude of negative wind work can be amplified by having this SST wind coupling process. So in order to have a more full understanding of LC, maybe momentum flux or wind work, we need both LC, wind stress and heat flux measurement. So this is the work done by being done by a grad student in South Korea. I'm lucky to collaborate with, and we are looking at this surface current impact on both momentum flux and LC heat flux here. So she's looking at the crucial current here. So this is wind stress formulation. Wind stress depends on relative wind, and this is a heat flux computation based on relative wind. And then in this particular case, surface current is going like this, and wind is looking at this coming from the south. And we are looking at the maybe 12-hour or 6-hour after the initial condition. This is right after the initial condition. So there's no significant feedback by large scale. So we can reliably say that whatever the change they were looking at is due to surface coupling impact. So we can do that by looking at the model output right after the initial condition. And you can see that wind is coming from the south, and this part of the current going northward against the wind. So there's an increased stress, and this part of the current where current is aligned with the winds, stress is reduced. So this is what we expect, right? Based on this bulk formula. And the impact of that is that the wind does feel this. So lowest level wind is reduced because there's a higher drag there, and wind is increased because there's a reduced drag. So you can reliably say that this is due to, again, drag momentum coupling involving surface current. We can do the same thing with the surface heat flux. So in this case, latent heat flux. Latent heat flux is anomalously out of the ocean. It's anomalously reduced because of wind speed wind is in opposite direction of the surface current. Sorry, so anomalously out of the ocean because relative wind is higher when the wind and surface current is opposing each other. So when you have a wind speed, surface current speed is like say 10% of the wind speed, you get the 10% increase in latent heat flux. There's a linear relationship. So the higher latent heat flux when winds and surface current in the opposite direction, reduce latent heat flux when winds and surface current are aligned, same direction. And you can see this surface air temperature does feel it, although this is a tiny magnitude, but there's an indication that air temperature can feel this air temperature surface heat flux response. So of course, Ajin is looking at this for the long-term simulation, so impact on the long-term large-scale Kuroshio impact on the storm track in this region. So this is my work of the Gulf Stream region. So we are looking at a similar thing. We are looking at the output like 12 hours after the initial conditions, right after the initial conditions. So whatever the response we're looking at is mostly due to Gulf Stream impact or maybe stochastic nature in the atmosphere. So we are using coupled model, two simple simulation, relative wind experiment where wind stress is formulated with a relative wind, and absolute wind simulation with using the absolute wind without surface current impact in the stress formulation. So what we are looking at is one particular snapshot again here. This is a wind work, so tau primes geostrophic wind work, so tau primes geostrophic current. So you see the very strong geostrophic wind work going into the ocean because wind and surface current is aligned in this case. The blue is the surface wind stress geostrophic current vector, and orange is the surface geostrophic current vector, and the blue is a wind vector. So they are in this part near the Gulf Stream, wind and surface current is aligned to the northward in this case. So wind work is done by wind to the ocean, so Gulf Stream is accelerating. You look at the difference of wind work due to relative wind effect, you get this negative wind work, negative changes in the wind work. And this is, we all know that from many papers, myself and Lionel's paper, the Gulf Stream receives less energy or energy is diverted from the Gulf Stream to the winds. So this will actually enhance the surface wind. And this is actually happening. So 50-meter winds, this is our lowest level wind in the atmospheric model. If you look at the wind speed difference between two simulations, there are a lot of KR variability here in the convective regime, but away from that, you see this very robust increase in surface wind at 50-meter height. And this is consistent with the negative wind work. So work is done by current on the wind. So there's a relative sense increased wind speed if you take into account surface current impact in the coupled model. You may say that, is this due to surface heat flux or surface really drag impact of the surface current? And when you look at the surface heat flux changes, and because wind and surface current is aligned in this case, there's a less heat going into the atmosphere because relative wind is lower, so heat flux is lower. So the fact that wind is higher is not necessarily in this particular case because of heat flux, but mostly due to drag impact, is wind work impact. So if you look at this little tiny box here and look at the 3-hourly evolution of the wind profile between two simulations, you can see this, right? So this is a boundary height is about 1,000 meters in this particular case. Right at the surface, 50 meters, you see this response difference begin to emerge about, I don't know, 6 to 12 hours. And this difference is 0.5 meters per second persists throughout the whole, in this particular case, 48-hour period, right? And the difference reach up to 100 or 200 meters in this particular case. So this is kind of robust feature that the surface current does contribute to wind profile. In this particular case is through the modulation of surface drag. But in this kind of area, we are very highly chaotic region. Even after 12 hours, things become extremely noisy because of convective variability in the system that can be chaotic and can be different between two simulations, right? So this kind of response developed matter of hours. And I argue that this kind of regime, you need this kind of variability mostly due to spatial variability in air-sea heat flux, not the momentum flux necessarily. So here's a big question that I'd like to ask. we know that people like us, oceanographers, look at this relative wind effect on the kinetic energy and the mean circulation, and we all show that if you take into account surface current, you reduce the wind work, and eddy kinetic energy is reduced and current slow down. And this is very oceanographic problem. And the meteorologists, like I showed in the previous first slide, people take the SST anomaly and perturb in the atmosphere and they look at the atmospheric response. In the Gulf Stream and Crucial region, the SST anomaly related to this western boundary current is usually the kind of the forcing of the atmospheric matter. And this is, again, very atmospheric problem. Atmospheric storms are influenced by their interaction with the ocean, and that is due through the LC turbulent heat flux coupling. If you look at the western boundary current, because LC heat and momentum flux is very strongly coupled, as I talked about in the tropical instability wave example, question here is that can this relative wind effect, so wind relative surface current or affecting surface stress, can it influence the storm track or other types of large-scale atmospheric variability, especially in the western boundary current region? And I think the answer would be yes, because if you change LC heat momentum flux, ocean will respond, and we all know this from this number of studies. And when the ocean responds, SS anomaly will emerge, and this anomaly will influence the large-scale atmospheric variability in regions like western boundary currents. So, so I guess this combining the two somewhat parallel problems, right? Ocean problems, atmospheric problems. You can answer this beginning to answer this kind of very fundamental question, like what is the role of ocean in the storm track or atmospheric weather variability through both momentum and heat flux. So this is hourglass current. Color shows the storm track variability. So again, you see the maximum storm track near the strong regions of the sea subtemperature front, and also hourglass current here, retroflux right here. We argue that this is also potentially important area where SS anomaly induced by the this relative wind effect can influence large-scale storm track. So experiment is extremely simple. Two different simulations: relative wind experiment where stress is formulated with a relative wind, and absolute experiment where stress is formulated with the absolute wind alone. And then we run long enough time to see the impact on the large scale. So here's the ocean response in regions where I see the largest response here. So kinetic energy from the relative experiment, and this is difference between two experiments. And you can see the kinetic energy reduced everywhere. And this is, again, consistent with many studies, including Leonard's papers and my papers. Many others' papers show the sort of eddy killing effect, eddy kinetic energy damped by the relative wind effect. Sea surface height anomaly shows that in this case, the striking feature is that there's a standing anticyclonic eddy here, about 25 degrees east, which many climate models tend to be too strong that it allows the hourglass current to prematurely retroflect eastward. And this anticyclonic eddy, this kind of bias feature is reduced in this model with a relative wind effect because all the circulation is slowed down and eddy is damped by this relative wind effect. Consequence of that is that this weakened anticyclonic eddy allowed the hourglass current to transfer more warm water into the main retroflection region. So you have a higher heat content here, higher sea subtemperature here as a result of relative wind effect. And then if you look at the cross-section here as a function of latitude toward the south, color shows the temperature changes. So again, there's a large opposition temperature increase, and the isotherms are pushed southward. So this indicates the SST gradient in this region is also strengthening, so about here. So we have two conditions here: warmer SST in this region and the higher sea subtemperature gradient in this region as a result of relative wind effect. And this is sufficient to satisfy this increased storm track activity by this baroclinic instability metrics. So what I'm trying to look at here is that ED growth rate at 850 millibar. Again, this is about 2 kilometers above the sea surface. So sigma sub bi, this baroclinic instability, baroclinic ED growth, ED vector. So this is ERA5 ED growth rate climatological, and this is model simulation. So they look fairly similar. And then this is a difference between two simulations as a result of change in SST and SST gradient in this region. You see a highly significant increase in ED growth rate in this region, where forcing is the largest. And there's also some indication of the increase in ED growth rate elsewhere, but these are not very significant response. So only significant response is found in this agarless retroflexion region. And you can separate this effect, change in baroclinicity solely due to temperature gradient changes or solely due to static stability changes. You can see that in this region, I think both contribute nearly equally. Somewhat different spatial pattern here is warm SST directly increase the decreased static stability and increase the growth rate of the baroclinic eddies. And do the same, also same thing here is increased gradient also does the same thing, but slightly different in the spatial scale. So this is my final slide. I want to look at this atmospheric response in these two simulations. And it's very challenging. If you look at my paper, there are a lot of, I made a lot of attempts to assess this objectively storm track response, only to realize that not many storms are actually passing over this box where we have a very strong forcing of SST anomaly. So I had to subsample these storms that directly pass these regions. So what I did is I averaged this box turbulent heat flux, two different simulations. So this is example here, normalized turbulent heat flux, two different simulations over this purple box. And then I sampled those storms that are strong enough and they feel directly over the increased heat flux out of the ocean is purple box. So red is a relative wind experiment, the blue is an absolute wind experiment. They are largely similar in terms of phasing, but there are important changes in the magnitude. So you can already see that in the relative experiment, the storms tend to be stronger. Whenever it passes over this box, it feels a higher SST, higher temperature gradient. So if you sample all the storms, average over storms exceeding -1 standard deviation, I have about 80 or 90 storms over 5-year simulations, and I do the lag composite of those storms. So this is what I did here. This is a relative experiment, control simulation, 500 millibar geopotential height anomaly. So this is onset of the storms. Onset I define here is a peak magnitude of turbulent heat flux. And I went back 2 days before and 1 day after and 3 days after. So this is sort of life cycle of atmospheric cyclones in the mid-latitude. So you can see these blue mean cyclones passing gradually over here. And then when day 0 corresponds to backside of the cyclone where heat flux is very large. And then over time, it passes eastward. So this is classical baroclinic eddies in the atmosphere that has a time scale between 2 to 7-8 day time scale. And this is a difference between relative wind and absolute wind experiment. And color shows a difference in the geopotential height anomaly. And interestingly, the large-scale patterns are again similar. So this does indicate to me that large-scale storm track activity is governed by large-scale atmospheric variability. But when they feel this localized SST forcing, they tend to be enhanced. In this case, when the storms feels this heat flux over this purple box, they tend to be enhanced. The enhanced is about 25% higher in the relative experiment compared to absolute wind experiment. It tend to maintain this strength about day 1, day 2, and about day 3, it loses significance. So about day 1 to day 2, each time scale, heat flux storms feels this heat flux and keep this energy into the downstream. So this is one indication that storm track can actually feel the small change in SST heat flux brought about by this relative wind effect on the circulation. So this is final slide. I hope I can make a kind of made a case here that we know that thermal and mechanical coupling is inherently intertwined, especially at the much smaller ocean mesoscale or sub-mesoscale. And we are looking at these two potentially important satellite missions that is being developed by the community, one by REC, through REC, which aims to estimate the accurate momentum flux estimate, but it requires turbulent heat flux, right? And also surface wave as well. Cesar Salvage, my postdoc, talked about surface wave impact a few weeks ago. And I think that's one important area that we need to improve surface wake impact on surface roughness and drag coefficient. Butterfly mission that I'm involved in is to aim to have an accurate global scale turbulent heat flux estimate, but it also needs surface current because relative wind effect is important on surface heat flux, and we need to have surface current estimate in this estimate. So these two satellites, if fly together, will likely stimulate, in my view, the new pulse of research on surface momentum and heat flux at fine spatial scale. So this is very exciting time for us. Especially modelers like me who look at this impact through the modeling study, then where this kind of data set will be extremely useful to further understand this multi-scale nature of the ocean current impact on the climate system. So this is all I have, and I'll be happy to answer any questions.
Thank you, Hyodae. We've got a question from Rick. Would you like to ask your question, Rick?
Yeah, sure. It's just a kind of a survey, and I'm not trying to put anybody on the spot. So, feel free not to respond to this. But if you're comfortable, I mean, the reason you might not be comfortable is that we're spending a lot of time and energy constructing satellites and taking good measurements, really measurements, as best as we possibly can. It's intuitive to call them nonlinear. So that's what I'm asking, is if people are comfortable considering, that we are somewhat restricted in our in the measurements that we can make, as expensive or as difficult as they may be. But it's not a question maybe to be answered right away, but maybe just to be posed without any, without any immediate response at all. But I throw it out there. It's just to have it considered. And in addition to considering that there are clearly some really interesting nonlinear associations to be made between the observations that we have, the ones that that Hyodae is showing throughout his talk here. This is all great. This is all what we're after. It's just we are constrained to some extent by the measurements.
Yeah. So
anyway, I throw it out there.
Yeah. I think yes, I think you broke a little bit, so I missed part of your question, but I guess so. For example, butterfly, when it flies, when it's approved, we aim to have like our year and a half operation of the satellite. So it's obviously very short, right? You can have 2 winters, for example, of these measurements. So this kind of very stochastic nature of the atmosphere, if you are trying to assess the large scale impact, it's not sufficient, of course. But still, you have a very good chance of understanding drag impact very well, and then validate the impact that is simulated by the model. Because all those model simulations that dominate this field of this mesoscale interaction, they are not very validated well, because we don't have data, right? So I think understanding this impact and how good they are, I think it's a very important step. And then if you have a little bit of confidence in this model, then you can begin to assess the large scale impact. Again, there's a fundamental stochastic nature in the system, but I guess the high resolution, very large ensemble simulation that we can do probably, or multi-model simulation, it give a little bit of sense of confidence in terms of response that we can see from just resolving these small scale errors interactions. So I'm not answering any question to you, but just I think models and satellite observation can go together, and as well as in situ observations.
I would agree with that.
Yeah.
Thanks.
Hyodae, while folks are asking more questions, I was wondering if you could comment on the status of Butterfly and what's the plan moving forward.
So, well, we submit the proposal. We were not lucky enough to get selected last round, but it's EVM3. So we are looking at the next call, which we don't know when will be. Maybe Tony might know. So we are preparing for the next round. And when it flies, we are thinking about mid-2030s, mid-ish to fly. And I think that might overlap with REC as well. So there's an opportunity to fly together, and I think that would be amazing if you have coordinate that way to fly these two satellites together. And Harmony might be flying around that time, so we might have a good chance to even look at surface wave as well. So it's an exciting time.
Sort of like building on that question, do you have any thoughts on like, because even if the missions fly together, the measurements wouldn't necessarily be simultaneous. Do you have any thoughts on how important would it be to have a lag in both time and space to collocate those observations?
Yeah, that's a very good question, because we are looking at the different strategies to measure this. I think at least for the LC heat flux, our idea is to have like co-located airs or all the state variable measurements at 15 kilometer resolution. So that's actually much better than what we have now, right? With all all those greedy product that put all those variables together into box regardless of time of the day. I don't know. Again, I'm not very involved in Odyssey, so I don't know what is the sampling plan. I just realized this 2+ has to be switched. So Odyssey is here, Butterfly is here. So it's a bit, yeah.
I just meant like conceptually, even without thinking of the missions itself, like to understand this difference between the response to heat flux and momentum flux, how apart in space and time things could be in such a way that you could still understand better this problem.
That's a good question. Yeah, I don't know. I think we know that this turbulent flux response is very rapid because, for example, TK production of this or Boyens production by shear terms or Boyens term. Sorry, TK production by shear term or Boyens term can be very rapid, right? And I, from my simulation, I saw that like maybe hours of response, right? It's already become extremely chaotic. Yeah, so I guess I don't know exactly how to answer the question, but I think we are talking potentially about very rapid timescale response in the atmospheric boundary layer.
Yes. I saw a hand up, but then it went away. I don't know. Does anybody have questions?
Yeah, that was my hand. This is Tony. I was going to address your question about the simultaneity of the different parameters for the two missions. So the simultaneous wind and current measurements are needed to study the mesoscale wind work. Whereas for the butterfly's case, the simultaneous SST temperature, humidity, and wind speed measurements are needed for the flux estimate to reduce the sampling errors. So it would be great if both the wind and currents and the other state variables for the flux estimates are all simultaneous. But we don't know that to what extent it will help improve the process studies. So therefore, I think it will be very important for the community to help make that case, whether it's needed or not, through some OSCEs. I'm not necessarily talking about data simulation, just a high resolution model, such as the ones that are being run by Hyodae, just offset some parameters and to see what is the impact. So yeah, we'll love to see that kind of results to help make the case for the different missions, not just between Butterfly and Odyssey, Harmony and other missions as well.
Do you have more questions? Got a hand up from Melanie.
Yeah, hi. Thanks for the really interesting talk, Hyodae. I was wondering, even though I agree with you that to fully understand these intertwined thermal and mechanical coupling processes, it would be amazing to fly both these missions at once. They have to be, because of the cost caps, I guess they have to be proposed separately. And so they have to be able to stand alone. And so I wanted to get your thoughts on a couple of ways we've been thinking about how to separate out the mechanical and thermal coupling effects. And maybe Mark, Barasa, and Tony can chime in here. But so one aspect is in your figure with the tropical instability waves from your longer ago paper, where you were showing that it's the winds. Yes, exactly. Do you think that by looking at the response only in certain directions relative to SST fronts, that it will be possible to separate out the wind current coupling from the SST wind stress coupling in the local case? And then I'll just ask you my whole question now. And then in your, I forget if it was before or after this, where you showed in your nonlinear effects in your coupled model, they're really far downstream effects on the storm track. And you said that, so it was a slide kind of like this, but it was a different one. And you said that the really far field effects were not significant. It's still a different one. I forget which one, sorry.
Yeah, so yeah.
Yeah.
Yeah, I know. Yeah, so I think this is the one. Yeah.
Yes, this one. And so you said that the downstream response by this mechanism is not significant. So then you think that will make it possible for Odyssey to see the wind current coupling downstream effect without it being intertwined with the heat flux effects.
Yeah, so the fact that the downstream response is not significant is probably because of multiple factors. Again, the stochastic nature in the system also has a lot to do with the model setup that I have here. I'm using regional model, and it's not a global model, so I think that's one of the important region that I don't see, because this boundary condition is prescribed here, right? So if you use global model, you might see somewhat different response because it's more freely evolving atmospheric circulation. It might get worse, I don't know. So it has to do with a lot of model experiments configuration as well. But it also has to do with the stochastic nature in the system. You may need hundreds of ensemble simulations to say something about significance in the storm track, for example, which is rarely done. I use, I think 40, 50 ensemble members, and I still see very little significance. So this is just tell you, basically, in the testament of this, how stochastic the system is. I don't think satellite will tell you about whether the response is significant or not. It's with model, only model can do that, right? But satellite can constrain that forcing in the response, or forcing in this in the important region, like in this particular case, Agorlas return current region, right? So if you can constrain that well enough, like heat flux response to given SS normally, how accurate it is in the model compared to observation. Windward changes in the model compared to satellite observation, how good they are. I think things like that will be very important in my view. I didn't really get the first question. So if you look at the wind in the direction of SST gradient, can you elaborate a little bit more?
Yeah, it's what Mark is saying in the chat. I'll just maybe Mark wants to read his comment. Oh, he's changing his headphones. I'll read Mark's comment. Mark says the SST response. Oh, here he is. Go ahead.
So the SST response is a sinusoidal function of the angles between the SST gradient and the wind vector. So you can select angles where the SST response is a maximum or zero or negative, and you can isolate. You can separate the two conditions. So the current response is not a strong function of angle. So you can pick conditions where the winds and the SSTs are such that the SST response is tiny, and pick the current response. But it's hard to isolate the current response from cases where the SST is strong. So there are complications from an Odyssey or from a butterfly perspective in separating the two processes.
Yeah, that's a good idea. I haven't tried that, but I guess yeah. So this is SST gradient, crosswind and downwind component, and wind vector, wind response, like in terms of current divergence, right?
Right.
Okay.
Okay, so I'm taking it, Hyodae, that you don't think that's a ridiculous solution to the problem of trying to disentangle the two for the purpose of Odyssey standing alone.
No, I haven't done. I actually cannot make many educated guess about how viable that might be. So
Okay, not that I thought it was ridiculous. That was the wrong word to use, but okay, thanks.
All right, do you have more questions or comments?
Oh, actually, I have another question. I can't tell if anyone is raising their hand. But
no, it's fine.
Yeah.
No,
Hyodae, can you go back to where you did the composite average over the storms crossing across the tip of South Africa? Yeah, that was interesting. Thanks. I guess I was trying to understand whether it seemed like you were saying that the strength of the storms in the left column, the enhanced strength, was a response to the heat fluxes over the Agulhas. But it seems like in the top panel at day -2, if you compare the low in the left and right columns, it's already stronger before it gets there. So is there some kind of larger scale response going on, or why is it always already stronger before it gets to your box?
yeah, that's a good question. I think I actually in my paper I look at minus day 3 or 4, so I think I even look at further, and I think there were kind of some indication of this. These storms are not just like isolated system go like start from here in the beginning propagating eastward. This is a kind of continuous stream of the system, right? And then if you have this storm already, it begins already. I think it already feels the heat flux response someway. So I guess that's one way to put it. And I guess there might be some slight large scale changes as well, because you're looking at the whole 5 years of extreme events. But yeah, that's a good question. But generally, this is not very significant either, right? So it's not very, statistically, there's no confidence in this response. Only when you reach day 0, you have a very strong significance. So this could be like filtering effect that can begin to emerge to as a significant response, but it has to do it from minus day 2, right? Because the way this 2 to 8 day bandpass filtering is working. So it could be statistical artifact or something.
Gotcha. Okay.
But I think I will weigh more in this the gray dots, which is significance of the response, and so it tell you about the confidence of this response.
Yeah. Oh, I missed the gray dots. Okay, thank you. And is that a similar story for early on where you showed the enhancement of the storm track over the Gulf Stream, and there's some enhancement upstream over the land as well?
You're muted, Hyodae.
I have a background noise going on here. Because we are looking at the large scale system, if you change one location, you cannot expect only downstream response. There's got to be upstream response as well. So in this case, you see this a very large response here and here, maybe somewhere here, Gulf of Mexico, which is unrelated to. So this is kind of one example of stochastic nature of the system, or maybe some dynamical explanation for this. But so usually you see this upstream response as well as downstream response. I think as a scientist, I try to have a good explanation. If you have a good explanation about this, then I feel good about it. If I don't have a good explanation about it, then I don't spend too much time on this, try to understand this behavior because of so much chaotic nature in the system.
Thanks.
Okay, let's thank our speaker again for a fantastic talk. And I'll see all of you next week. Thank you. Thank you, Hyodae. Thank you very much.
Thank you, Hyodae.
Thank you.